in this lesson, we are going to go over optimization problem. After we learn the first and second derivative test, we can use the derivatives to find the maximum value or minimum value. So this is how we solve the optimization problem. So first, we have to draw any pictures and write equations, whatever we are trying to minimize or maximize. Next, we are going to take the derivative basically and set equal to 0, sign chart, and make sure it's max or minimum value. For example, 1. So after we read the problem, this is the box. We cut 4 corners, and we are going to make a box with the bottom here, and the height is x. We are trying to maximize the volume. So if you look at the final box, the volume is given by base area, 12 minus 2x times 12 minus 2x, that's the base area, times the height x, this is our volume. So take the derivative. So here, don't FOIL, as I said, don't FOIL, and factor. So we set equal to 0, find the critical point, sign chart, and at x equals 2, give us the maximum value. The volume will be 128. So example 2, if you look at this one, what dimensions we are looking for to maximize the area here. So if you look at the dimension of this rectangle, we have 2 variables, x and y. So the area for this part will be x times y. However, the function in calculus BC, we have to express the function using one variable only. So we have to find a relation between x and y using the given condition, 50 feet. So that means x plus 2y. So all the sides add together give us 56. So x plus 2y equals 56. We are going to solve for x, replace x using 56 minus 2y. Now, area is expressed using one variable only. First equals 0. To the sign chart, find the maximum minimum value. So if you look at this one, what's the dimension? Give us minimum surface area. So if you look at this box, the dimension here we need, because the base is a square, so we only need one variable for the base, and the height we need one variable, so 2 variables. The surface area is given by the base 2x squared times 2, top and bottom, x times y, the 2 sides, and x times y, the front and back. So this is the function. However, we have 2 variables. We have to find a relation between x and y. We use the volume. The volume is given by A64. So x squared base area times height. So we solve for y, plug it in, change the problem, the area, into a function of one variable only, x here. So derivative, sign chart, and maximum minimum value. So if you look at example 4, this function, a rectangle, is bounded by the x-axis and the semicircle, this one. What's the length and width should be the rectangle have so that the area is maximum. So we are trying to maximize the area. So the area function is given by, so if you look at what dimension, so if you look at the length, so this is the length and this is the width. So because it's symmetric, we are going to call this x, this is x, so the length will be 2x and the height is y. And of course you can define this as x2, but that will be a little bit more complicated because you have to divide by 2 in the future. So this is x, this is y, so the area is given by 2x times y. What's the relation between x and y? If you look at this point, the coordinate for that point is xy basically, and that point is on the semicircle. So y equals square root of 16 minus x squared. Then take the derivative, equals 0, critical points, and do the sign analysis. Next one. the cost function. So given this cylinder and each side cost differently, so what's the dimension for the can that will minimize the cost? So if you look at the dimension, how many variables we need, because the cylinder, we need the radius and the height here. So the cost function will be $3 times the area of the wall, which is the side, 2 times the top area, 7 times the bottom area. And the wall, as we know, the wall will, when we open it, it will be a rectangle. The perimeter of the circle times the height, basically the length times the width, plus 2 area because they are circles. So now the cost function equals this, and we have two variables, h and r. We have to find a relation between h and r because the total volume is 105. 105 equals pi r squared times h. We solve for h and plug it into the cost function. So now we change the cost into one variable, r only. Next, we just take the derivative and do the sign analysis. Let me go over one more problem. So if you look at this point, this problem, find the point on the graph y equals this, closest to the point 3, 0. Okay, so we have a graph. We have 3, 0 somewhere. So if you look at the point, as the point is changing along the curve, you see the distance between the point on the curve and 3, 0 is also changing. So which one is the shortest distance? We are trying to minimize the distance. So first, we have to find the distance between any point xy on the curve to 3, 0. So the distance equals square root x minus 3 squared plus y minus 0 squared. Because this is always positive distance, it will be much easier to minimize d squared instead of d. We don't want to include the square root. If d squared is a minimal value, then square root will also give you a minimum value. Okay, so this is the function. Now we have two variables, x and y. Now we have to find the relation between x, y. Keep in mind, x, y is a point on the graph. So y equals square root of x plus 1. We replace y here using square root of x plus 1. This is our function. Derivative equals 0. Sign analysis.